and this work in conjunction with my colleague Chris Schwab as part of our EU project. I'll make sure the slides are available later. If you can't see all the details down the bottom, that will be fine. So let me introduce the problem. The problem is that we need to control robots in a human understandable way. And the state of the art, unfortunately, is largely one where robots are programmed to do specific things, but we have very little understanding about exactly what the robots are doing and whether or not the things that they're supposed to be doing are what they actually do. The robots need to be flexible, they need to be easily changed, they need to adapt to changing situations, which means that having a fixed program is not very effective. What we want to be able to do, and this is work that goes back ultimately to the 1960s, work on Planet, etc., is to generate plans for actions that the robot performs. Unfortunately, we need to know that the plan does what we want. We need to know what happens if the plan fails. How do we recover from failure in a robotic situation? And, of course, what happens if the robots start to take over the world? And I'm not going to cover that in this talk. That's the topic of the next talk, if we're still here. So first, let me introduce you to the idea of AI planning as seen from 30,000 feet from my aerial drone. So the first thing we have to do is describe the possible beliefs about the world in terms of some kind of planning domain. We then need to describe the set of actions that can be performed, set up the initial state of the world, give the desired state of the world at the end of the actions, and then, based on that, what we've got to do is we've got to find an action sequence, that is some plan, that takes us from the initial set of actions into the final set of actions. Now, you're all good functional programmers, and you should all realize, wait a minute, this sounds a lot like the sort of things we typically do in functional programming. We're rewriting from one state to another. We start in some initial state, the goal of the program, and we end up in the final state. And that is exactly our idea too. So our key idea is that at the moment, plans are given as logical specifications. There are some well-defined planning languages. I'm going to show you one later on, something called PDDL, a domain-specific language for planning that is used in the AI community. Functional languages are, of course, very good at executing logic. Do we have any logic programmers in the audience? Okay. I would go as far as to say functional programs are better at executing logic than logic programming languages are. And you'll understand why if you've used logic language. Types and type checking. So if you have a type-based language, something like Haskell, what you have built in for you, in addition to the usual functional evaluation engine, is your own logic engine, which has been refined to the extent we can now do some incredibly powerful kinds of logic reasoning automatically through the type inference mechanism of a language like Haskell. Or if you're coming from the Erlang world, maybe you don't have it built in, but you still have some kind of type checking engines that you can apply to your programs, and which can do much the same thing. So the work that Costas Sagonis has been doing, for example. Functional languages are very good at giving specifications. High-level declarative notations help with this. Higher-order functions are also good for this. But they are also good at running real programs. And this is a real edge. You can have your cake and eat it. I was on a project proposal once where we were trying to describe specifications in some language. And after about a month, I realized that what I was writing down in Haskell was what the other guys thought we were going to be doing in the specification. But I could run my specifications, as opposed to simply writing them down. So if we can define a domain-specific language for planning and a type checker in a functional language, such as Haskell, then we can automagically verify the plans that we derive, so we can ensure the plans succeed, they carry out the actions that we expect, that the systems that we produce end up in the right state, and there are no unexpected failures. And moreover, we can actually run the things, which is brilliant, without any of this magic translation into some other programming language that happens with the current state of the art. So let me give you a very simple example. Here is one of this is basically Noddy's first planning example as shown in the textbooks. This is something called Block's World. And basically what we've got is we've got a robot with an arm, a robotic arm, and we've got a series of blocks which are placed on a table that the robot will pick up and can put on top of each other, or pick up and put on the table, etc. So very, very simple example just to illustrate what we're doing. The first thing you have to do is to define the objects in the world. So I'm going to ignore the robot. For some reason, they always ignore the robot as an object. Doesn't quite make sense to me as a functional programmer, but I'm sure we'll get deeper into this. So the objects that I have, the things I can manipulate, are A, B, and C. 3 blocks, block A, block B, and block C, which are currently on my table. What I then need to do is to find some beliefs about my system. So, for example, the beliefs might be that the hand of the robot is empty, or that it's holding block A. Or that block C is on block B, and block C is clear. There's nothing on top of block C. So these are all facts and beliefs that I can define. So we have C on B, clear C. We might also have that A is clear. There's nothing on top of it. So that's a standard predicate. And then we also need to say, well, actually, it's not good enough to have these blocks sitting in free space somewhere. They've all got to be on the table, because otherwise this block world doesn't make any sense. So given a world like that, what we're trying to do is to define some actions in this high-level DSL. These will be actions like picking up a block. So given some preconditions, the hand should be empty, the item must be on the table, the item must be clear. Having picked up the block using the robot, then we know from the post conditions that the hand should not be empty, the item is no longer on the table, but the arm is now holding the object, as we'd expect. So the robot has picked up the thing from the table, and it's holding it. All very, very simple. And this is how you would express that in this planning language. You start off... Peter lost the microphone. We start off with the hand empty. We have A on the table and A clear. And we end up, and sorry, the red is not showing up properly on here, but we end up with the robot holding A. We end up with A not being on the table, and we end up with not hand empty. So this is a complete specification of the state that we expect, having carried out that action. In addition, what we then need to do is set up the initial state for the world. And again, there's a closed world assumption with a lot of these planning languages. One of the things that we need to start to think about is how do you go beyond a closed world assumption where you know about every object in the world, you know about everything that could happen, to a much more open space where there could be objects entering your world, there could be dogs wandering around that you don't want to pick up, and so on and so forth. So the initial state might be that A, B, and C are on the table, and there's nothing on A, there's nothing on B, and there's nothing on C. So the goal state that we want to end up with is that A is on B, B is on C, and of course these are on the table. So we're trying to go from that initial state to the goal state like this. What we want to do is to form some actions that are going to stack the blocks. Everything else is going to be left unspecified in the planning language, including what happens on failure. So we need some way to reason about it, but we don't want to have to specify explicitly what happens on every possible failure, because there are just too many things that can go wrong. And we need to find a plan that's going to take us from that initial state, the blocks on the table, to the final state, the blocks being stacked. So, for example, the plan might be we pick up block B, we put block B down on block C, we pick up block A, and we put block A on top of block B. So, Does that plan work? Audience question. Who thinks it works? It can work. Yes. Is it the only possible plan? No, there are many, many possible plans. Well, what about this one? Pick up A, put A down on C, pick up A, put A down on the table, pick up B, put C on B, pick up A, put B on A. Very simple plan, but already you're having to think about what's going on, right? Is it the same as the previous plan?
What do you mean by same?
Very good question. I mean what I say I mean. By same, what I understand in the AI world is the final state, the final goal has been achieved. The plan carries out a set of actions that takes us from the initial state and puts us in the final state. So who thinks it does that? Hands up. Who thinks it doesn't do it? Who isn't sure? A few of you. Okay, be honest. It's good. It's good. Okay, so it's already a bit complicated. Now, I can say to you that this verifiably does the same thing, but doesn't do it nearly as efficiently. Because you're picking up a block, you're just putting it on block A, you're putting it on block C, you're taking it off again, and then you do essentially the actions you had before. So the two are provably equivalent, if you could go to that trouble, but not immediately obvious just from looking at the plan that they are the same. And that's something very, very simple. So what we want to do is to verify the plans. And our idea is that beliefs about the world state should become types, that the actions are function types that move between states, and that some function from the initial state to the goal state is intrinsically correct. So what we can do is create a sequence of actions captured up through the types, and that will then allow us to reason about the final state, essentially doing some sort of state transition analysis through the type system. Very importantly, and in contrast to a lot of work on verification, we don't care how the plans are produced. All we really care about is that what the plans do. So as long as you can verify the plans do the same thing, we don't care whether you're using some really, really nice notation, Agda, Idris, whatever, or whether you're using some hacked together AI planning tool. As long as the plans are provably correct and we can express them, that's cool. And of course, we also need to allow for all possible failures, replanning or retrying. So I'm going to very quickly give you a sketch of this because I won't have enough time to go into it in detail. What we're going to do is we're going to map our beliefs into propositions relating to the world space. So these are the beliefs that we have. We're then unfortunately going to have to normalize things because the meaning of an atom changes depending on the context. And particularly you could have a negation, you could have a double negation for some atomic action. And you need to account for that. So we do this using a series of standard rewrite rules. We then have a set of actions that we sequence into a plan. You probably can't see this, but this is formalized as a type rule that tells us that given the current world, the world is M, given that F, the first action, uses a subset of the facts in M, then we get a postcondition M2. All the M that are consistent with M2 will also hold. And after the execution of E, so following E and F, then postcondition N also holds. And therefore, by composition, by the rules of type magic, etc., having E semicolon F, E followed by F, then N will hold. And of course, you need a rule that says you get to the end and you throw away any unnecessary evidence which is still there, so you can conclude the proof. Okay, 2 minutes. This is what it looks like if you're going to define this using standard PDDL notation, so we have something that's a bit Lisp-like, we have a set of definitions, and we define all the predicates, and we define all the actions in a parametric way. And we were quite alarmed to discover how fuzzy some of these definitions were when we started to discuss them with some of the planning people. What we're then doing is to translate these into a functional language. So we're going to define a DSL, domain-specific language, where we have object types A, B, C, etc. We have predicates over the atoms, which will be conjunctions and negations, neg, and basic facts, atoms. And then the things we know about hand empty, holding the object's on the table, etc. We can then define some actions, pick up the object, put down the object, set up the overall list of actions that pick up, how the pick up and the put down are defined in terms of their preconditions and their postconditions using this DSL which I've just constructed. Define a plan. This is the plan I had initially. Pick up B, put down BC, pick up A, put down AB, start and find goal states. And now, using the fact that a proposition is a type, what we can do is to use type checking to verify that the proposition is always true. So we write a type checker for plans in Haskell, or you could use Erlang or Idris or whatever, where the checking function takes the actions, a plan, the pre and post conditions that we require, the initial and goal states, and gives the result back, where the result is, yes, it type checks, or no, it doesn't. If it type checks, it works, and if it doesn't, it fails. And we know that for sure. We know how it fails. And then we can check that. So we just run check action, so we run the check function with the actions, the plan, and the start and goal state that I've defined. I ran this in Haskell, this is what it spat out, and it said, yeah, that's success, and here's what you end up with. All of the conditions, all of the different things. So it's inferred all of these things for us as part of the type checking process. Great. So I'm going to skip over the soundness properties, but we can prove that's correct. And I'm going to conclude. So the conclusion is we can capture plans in an embedded functional DSL. Type checking DSL lets us verify the correctness of the plans using our own type checker. We obviously have to verify the correctness of our type checker, but that's a meta issue. We can show that alternative plans are equivalent because we can simply verify the equivalence of the final version of the plans using the soundness theorem. Failure is automatically encoded in the plans. I haven't shown you how, but the idea is to use something like a monad to encode it with built-in retry, etc. And we believe this is a good basis for doing future work on AI planning and improving some interesting properties that the community is very concerned by at the moment. What we're going to do now, we're going to work with an MSc student over the summer to put this onto one of Pia Stritzinger's GRISP robots. So Pia is probably running around with them today. Translate what we've done into Erlang, verify the correctness, encode replanning and retrying the type system, so we can then map that down into the actions that are happening, and we will then be able to capture higher level reasoning, epistemic reasoning, which is something that the AI people, the AI planning people are very, very concerned by, apparently. So that's all I have to do. Very early stage work, but I'm very happy to answer any questions you might have.